Hello there and welcome back. In the previous videos, we've been discussing how to conduct hypothesis tests for the population mean and the population proportion. In this video, we're going to be looking at how to conduct hypothesis testing via the perspective of confidence intervals for the population variance and the population standard deviation. So let's get started with a couple of assumptions that we need in order to do this appropriately or accurately. So suppose that we gather a sample from a normally distributed population with some mean mu and standard deviation sigma for which we do not know the value of. So let's just recall a couple things that we've discussed in previous videos that are going to be very useful here. So recall that if x is equal to x1 squared plus x2 squared all the way out to x1 squared, where each of these xk's are normal random variables, or more so standard normal random variables, then the sum of the squares of these standard normal random variables will follow some distribution. In particular, it will follow a chi-squared distribution with n minus 1 degrees of freedom. So if this is the case, then what can we do actually with this piece of information? So remember that there is a connection between this expression and a few of the metrics we've actually been discussing from the perspective of metrics of variation. So remember that the variance, s squared, is going to be equal to the sum of square differences for a sample divided by n minus 1, which remember is the sum of xk the quantity minus mean squared divided by n minus 1. So pretty much there, if we sort of ignore that x bar, that is the sum of squared variables that we're actually looking at here. So one can think, well, since x bar is typically a constant, xk minus x bar is simply a shifted version of this particular random variable x. So if that is the case, then the distribution should just be shifted versions of each other as well. So if we observe it from this perspective, we can actually multiply both sides of this equation by n minus 1, and then we have that the sum of square differences for a sample is going to follow the same exact distribution as n minus 1 times the variance of an arbitrary sample. So once you are able to conduct that observation, one can also observe, that sigma squared will be a constant. Let's assume that the parameters of the population are not changing. So if we divide both sides of this equation by sigma squared, then we have a scaled version of this chi-square random variable. So therefore, this variable, let's call it x, defined to be equal to n minus 1 times s squared divided by sigma squared, will follow a chi-squared distribution with n minus 1 degrees of freedom. So this is going to be the tool that we're going to use in order to construct confidence intervals for the population variance, because we have the point estimate and we have the parameter located in the same exact object, and we have a distribution to represent the distribution of confidence or statistical significance, which is usually what confidence intervals are based on. So let's just review what the chi-square distribution looks like. So since a chi-square distribution is simply just the sum of squared normal random variables, it's definitely going to be a non-negative distribution. So recall the graph of the chi-square distribution is actually skewed to the right? So let's assume that we want a two-sided alternative. So the null hypothesis is going to be that, null hypothesis is that sigma squared is equal to sigma squared 0. And the alternative is going to be that sigma squared is not equal to sigma squared 0. So let's assume that we want this two-sided alternative to be symmetric, so equally on the right and equally on the left. So when I say equally on the left, that means I want the area to the left of that number and the area to the right of this number to be equal. That is, I want this area and that area to be the same, right? So if I want that to be true, then I need to define two boundaries, which I'm going to call the critical values for this interval, which is going to be chi squared L and chi-squared r. Notice this is a little bit different compared to the t and z distribution because this is not a symmetric distribution. Therefore, it's not z critical value and its opposite because both of them are positive and one is significantly different than the other. So this area shaded in green, that's going to be our alpha, and this area shaded in teal, that's going to be our region of confidence, C. So how are we going to find these two critical values? So keep in mind, we have some formulas for them. This is simply the 1 minus c over 2th percentile of the chi-square distribution, and this is the 1 plus c over 2th percentile. For the chi-square distribution with n minus 1 degrees of freedom. So we should be able to find these critical values, and thus we should be able to construct a probability statement for the population variance. In particular, one can say that the probability that this random variable x, because what is x? X is going to be this random variable which follows a chi-square distribution. Therefore, if everything holds true, then the probability that x is in between chi-squared L and chi-squared R should be equal to C by design. Now that we have this, now we have some frameworks and tools in order to construct a confidence interval for the population variance. So let's just replace x with the definition of the variable that we know follows a chi-square distribution. So that means what? That means the probability that chi-squared L is less than or equal to n minus 1 times s squared divided by sigma squared. So keep in mind, s squared is the random variable in this expression, not sigma squared. Sigma squared is just a constant. That means this is going to be equal to chi-squared r, and this is going to be equal to c. Now, what do we want in the middle in order to construct a confidence interval? We want this in the middle. So we want this alone in the middle. And then we have something like, sigma squared plus or minus epsilon because we're going to have something on the left and something on the right, and that's going to give us what we want. So what we need to do is we need to get rid of this object. So keep in mind, n is a number usually bigger than or equal to 2. Therefore, n minus 1 is going to be a positive number. Variance is always positive. So we can technically divide both sides of this inequality by n minus 1 s squared, and we should get an equivalent inequality for which we do not have to change our direction of our inequality signs. So we're going to have chi-squared L divided by n minus 1 s squared less than or equal to the reciprocal of sigma squared less than or equal to chi-squared r over n minus 1 times the variance of our sample. This should be equal to c. Now, if I flip the interior, the other boundaries will also flip and also change positions. You should be able to test this conceptually on a smaller inequality. For example, 1/3 is less than 1/2. So if I flip both of them, is 3 less than 2? No, so these two numbers should be switching positions, and that's usually always true for real positive numbers. So when you reciprocate, of course, the boundaries reciprocate, but they also change directions because the inequalities will also change directions as well. So that's going to give us what? So that's going to give us that the probability, so the right becomes the left, so we're going to have m minus 1 times s squared over chi-squared r is less than or equal to sigma squared is less than or equal to m minus 1 s squared divided by chi-squared L, and that's going to be equal to c, and that gives birth to the confidence interval for the population variance. Now, please be very, very careful. Do notice that the critical values are in different locations. So these are mirrored. If you remember our discussion about one-sided alternative hypotheses, this should make sense as to why this might be the case. So once we have this expression, then now we can formally state our confidence interval for the population variance. So under some level of confidence C, so that's going to be a C% confidence interval for sigma squared. This is going to be equal to what? So the left boundary is going to be equal to m minus 1 s squared chi-squared r and n minus 1 s squared chi-squared r. So that is our confidence interval for the population variance. So how do I get a confidence interval for the population standard deviation? Take a guess. So we're just going to be taking the square root of these boundaries. So also keep in mind the square root of chi squared is not chi. Chi squared is just a representation for a distribution, right? So don't say stuff like that. So this is going to be equal to, so the square root of variance is going to be standard deviation, so I can write this as actually s times the square root of n minus 1 all over chi squared r, comma s times the square root of n minus 1 all over chi squared l. And keep in mind n minus 1 is just the degrees of freedom, so technically we can write this equivalently as c% is equal to s times the square root of nu over chi squared r times s times the square root of nu chi squared l. And this is the confidence interval for the population standard deviation, sigma. Now let us look at a couple examples on actually how to execute this particular tool. So let us suppose that someone claims that the standard deviation of the population of systolic blood pressures is 3.54 millimeters of mercury. If you take the probability of committing a type 1 error to be 2% with a sample drawn from a normally distributed population given by a sample average of 125.4 millimeters of mercury, a sample standard deviation of 4.1 mmHg, and let's assume that the sample size is 27. Based on this evidence, do we reject or fail to reject the claim that the standard deviation of the population is 3.54? So pretty much what we can do is we can calculate a confidence interval, see if 3.54 belongs to it, and that pretty much gives us some evidence to reject or fail to reject. So let's just formally state our null hypothesis. So the null hypothesis is that sigma is equal to 3.54, and let's just choose a two-sided alternative. In particular, sigma is not equal to 3.54. So we need a confidence interval for the population standard deviation. Since let's assume sampling from a normally distributed population, and I believe that is given to us, right? Yeah, so this population is normally distributed, which is great. That means we should be able to use a chi-square distribution to model sum of square differences with no issue at all. So this is going to be the distribution of our chi-square distribution, and since the sample size is equal to 27, that means this is going to be a chi-square distribution with 26 degrees of freedom. So what do we want? So we need to figure out what our boundaries are in terms of critical values. So we want this area to be equal to what? So we took alpha to be equal to 2%. That means this area should be equal to 98%. So that means we need to figure out these lower boundaries and this upper boundary for this confidence interval. So if we take v to be equal to 26, you should be able to find that the left critical value for a chi-square distribution is approximately 12.1981, and the right boundary for this critical value is going to be equal to 45.6417. If you're using Excel, you can find these values using equals CHISQ, so chi squared, dot IMV of 1 plus or minus C over 2 comma V, where minus is used for that and plus is used for that. So keep in mind that if S is 4.1, we should be able to find our variance. So S equals 4.1 gives us S squared of 16.81. So if you want to find the confidence interval for the variance, you easily can do so using this variance formula. But we're just going for the standard deviation. We have a representation for that, so we can get it directly. So therefore what? So the confidence interval, the 98% confidence interval for sigma, is going to be equal to the standard deviation times the square root of the degrees of freedom, and the degrees of freedom was given to be 26, all divided by the right chi-squared critical value. So that's going to be 45.6417, and then it's going to be 4.1 square root degrees of freedom left critical value, 12.1981. If you get these left and right critical values in the wrong position, you should get something like 5 is less than or equal to 3, or something that doesn't make sense, because the left boundary is going to be greater than the right one if you get them backwards. So once we have this, then we have a confidence interval constructed. So what will you get once we do out those calculations? That's going to be approximately equal to 3.09 and 5.99. So this is my confidence interval for sigma. So remember that the null hypothesis was that sigma is equal to 3.54, and 3.54 does belong to the relative center of this confidence interval. Therefore, we will fail to reject this claim. And that's how we use confidence intervals for hypothesis testing. Now let us take a look at how we would do this for the one-sided case. So suppose someone claims that the standard deviation in the number of hours of sleep that a person gets per night, or a population that people get per night, is more than 2 hours. So keep in mind, if the standard deviation for sleep hours is low, that means practically everyone is sleeping approximately the same amount of time. So if you have a variance that is really high for the number of sleep hours, then that means some people are sleeping little, some people are sleeping a lot. And if you know the distribution and the mean, then you probably can do some empirical estimates about, on average, people sleep between this hour and that hour, and so on. So let's assume that we want to test this claim, and let's assume that we choose alpha to be equal to 3%. So if we choose alpha to be 3%, that means we're going to be constructing a 97% confidence interval for the population standard deviation of the population, which is taken to be more than 2. So let's also gather a sample. So let's suppose that we gather a sample, and let's assume that the sleep hours are normally distributed, and let's assume that we do not know mu and we do not know sigma. And let's pretend that the sample that we get was a sample of size 35. Let's assume that the average was equal to 5.47 hours. And let's assume that the standard deviation of the sample that we obtained was 1.68 hours. So if this is the case, well, what would be our null and our alternative? So the null hypothesis is that standard deviation is greater than 2 hours. So the only reasonable way to go about testing this is using our one-sided alternative. Sigma is less than or equal to 2, and of course greater than or equal to 0. So we will reject the null hypothesis given what information? So we will reject the null hypothesis if the standard deviation of our sample is significantly less than the claimed value of sigma. So if we look in the standard deviation world, because remember, we have two equivalent perspectives of this test, right? So we have the standard deviations, or the variance perspective, I guess you could say. So the standard deviation perspective, so the standard deviation is chilling somewhere in here, and we have like S minus epsilon L and then S plus epsilon R, right? And that's going to define our level of confidence. So remember, we're going to reject if S is significantly less than sigma 0. So that means sigma 0 should be somewhere up here in order for us to reject it. So that means our confidence is everywhere to the left of some boundary which is chilling up front. Now, from the critical perspective, or the critical value perspective, so our chi-squared perspective, so keep in mind we have some number in the middle that's going to represent our standard deviation in the normalized world, and we're going to have chi-squared L there and chi-squared R there. So if our confidence is on the left in the domain world, our normal standard deviation domain world, that means our region of confidence should be on the right of the chi-squared world. So this is going to be equal to C. Therefore, the only number that we need to find is the chi-squared L number. If you get this backwards, eventually you will realize that something is not going to make sense. Let's see if we can pick up on where that would occur. So what do we know? So n is equal to 35. Therefore, this distribution is going to be a chi-squared distribution with 34 degrees of freedom. So what would our confidence interval look like? So our confidence interval looks like this particular world. This tells us which critical values we need. So the confidence interval, I guess you could say a right-tailed or a left-tailed, really depends on which perspective you're looking at, for sigma is going to be equal to 0 up to 1.68 times the square root of 34 divided by chi-squared L. Notice if this picture doesn't make sense, that means that's not going to make sense either, and then you're going to have a contradiction. So how are we going to find chi-squared L? So keep in mind, if the area shaded in red is C, that means this is equal to alpha. That means this number is the alpha percentile of this chi-squared 34 distribution, so you should be able to find that. So that means this chi-squared L value is going to come out to approximately 22.7093, and then we can substitute that into this confidence interval to get what we want. So our one-sided confidence interval is going to be equal to 0 to 1.9578. So that is our confidence interval. So remember, the claim was that sigma is greater than 2. Sigma is greater than 2. So notice that 2 is not in this confidence interval. Therefore, any number greater than 2 also is not going to be in this confidence interval as well. So since none of these values in this claim are in this confidence interval, we will be rejecting the null hypothesis in this particular world. Now, a fun conversation can be had. For example, what if somebody says that sigma is greater than 1? Well, some of these claimed values are inside of this confidence interval and some of them are not. So do we reject or fail to reject? That's a fun discussion to be had another day, but let's just assume that that's not the case here. So anyway, this is just an introduction to hypothesis testing on the population variance and standard deviation. I'll see you in the next couple of videos where we will begin to discuss how to compare different population parameters, for example, the mean, proportion, and variance. See you there. Take care.